Thanks very much, Anthony, and thanks to all of you for coming out at the end of the day to hear what I have to say. So if I can get this, yeah, here we coming up. There we go. Basically, I want to talk in several parts, about 4 or 5 parts. I'll start with the basic climate science and tell you what the science is really saying, despite what you might have heard in the popular media. I'll then talk a little bit about the risks that this poses, particularly for Australia, with some comments, of course, on rural and regional Australia and what it might be facing with regard to the climate change challenge. I'll then talk a little bit about the so-called skeptics or deniers, or whatever you want to call it, the group of people which have been very active in the press recently, who challenge the fundamental science of climate change. And I'll ask the question of, does this really constitute a credible alternative science of the climate system and how it's changing? And I'll close with a few comments on the media and the media treatment of climate change science. And then I hope you'll agree a few positive comments at the end about how we might meet the challenge that lies ahead of us. So let me go straight into the climate science itself. You may have heard quite erroneously in the press that global warming has stopped, that the last 10 years the Earth has stopped warming and so on. Well, the opposite is actually true. If anything, the rate of warming, the rate of change in the climate system has accelerated. This is the data set that a lot of people like to look at because it's the atmospheric temperature record over about half a century. This is the one from NASA, the one that most scientists use. And you can see that there's a lot of interannual variability from year to year. But over the last 30 years, there is no doubt what that trend is doing. It's going upwards at about 0.2 degrees Celsius per decade. And that trend has not slowed down one bit during the decade from 2000 to 2009. In fact, 2009, you can see it just here, was the second equal warmest year on record, surpassed only by 2005. And if we look at the mean of the temperature changes through this decade compared to the 90s and compared to the 80s, we see that each one was significantly warmer than the one preceding it. So absolutely clear evidence that the Earth is warming, and it continues to warm. And this is actually an exceptionally high rate of warming when you look at it from a geological perspective. But one thing that often gets missed out in the debate is that we focus on atmosphere, and that's because we're terrestrial creatures. And we're most interested in the temperature about 1.5 to 2 meters above the surface of the Earth, because that's where our heads are located. But if we were a marine mammal rather than a terrestrial mammal, we would be very much more interested in the next graph. This is an analysis of where the extra heat from the extra greenhouse gases in the atmosphere is actually going in terms of compartments in the Earth's system. These top bars represent the oceans. There is the atmosphere. You can see just by the length of those bars that massively more heat is being stored in the ocean than being stored in the atmosphere or in any other compartment of the Earth's system. In fact, if you really want one indicator of climate change, you go to ocean heat content or ocean temperature. That's where all the action is. Over 85% of the extra heat is going into the oceans. And you might ask yourself, has ocean temperature risen or ocean heat content risen? And is it accelerating or is it slowing down or stopping, as the skeptics might say? Well, the light blue bar is a 42-year record. It's from 1961 to 2003. The purple bar is the last 10 years of that record. And you can see that over half of the total heat content, extra heat that's been stored in the ocean, has come in the last decade of that record, which is strong evidence that in fact it's accelerating. There's the most up-to-date record of ocean heat content, and you see it was slowly rising through the 1950 to 1970 period, and now it's increasing, rising at an increasing rate. And notice from 1998 to 2009, it has risen quite sharply. There are 3 independent estimates of that by 3 different groups around the world, and I'm very proud to say that the gold standard, which is the one in the black, is actually an Australian group. It's a group of John Church of CSIRO in Hobart. And I'll comment a bit later about the quality of Australian science, but this is a good example of how, in many regards, we're right up at the top by world standards. But the point I want to make here is absolutely clear. The ocean is warming. It's continuing to warm. It's warming at a faster rate than it was warming half a century ago. We can have other indicators of how the climate system is changing. This is Arctic sea ice, and you see visually, when we first had satellite images from 1979 to 2007, how much shrinkage there has been in the area of sea ice. What this doesn't tell you is that the thickness is also diminishing quite rapidly. The top graph, this shaded area, shows you what climate models think the Arctic sea ice should be doing. And they see certainly that it should be diminishing as we go past 2000 toward the future, but even at 2100 there should be some left. The red line is the data, the observations of how fast it's actually changing. And you see a pattern here of agreeing with the models last century, but when we hit about 2000, a little bit before, the climate system starts moving faster than the models think it ought to be moving. So contrary to what you might hear, the climate models, yes, they're not always accurate. In many ways, they have some ways to go. But in fact, if anything, they are underestimating rather than overestimating the speed at which the climate system is moving. Here's another example that's very important for sea level rise. These are the big ice sheets that sit on in the polar regions. This one's in Greenland. There are also big ice sheets on Antarctica. The color coding here, the cool colors are where ice is accreting, where there's actually more ice because there's more snowfall. The areas in the warmer colors around the edge are where Greenland is losing ice. Bear in mind that this is about 2 kilometers in height, so it's much colder. Down at sea level, it's much warmer. And you get melt and also dynamical loss of ice along the edges. We now have instruments, altimetry measurements and gravimetric measurements, that can estimate the overall mass balance change in that ice sheet. And you see again, in the 1900s, it was about in balance, the zero line. It wasn't accreting or it wasn't losing ice. But as we go through toward the present time, you see a curve that's very similar to the Arctic sea ice. Slowly start losing ice, and then it's dropping off very rapidly over the last 5-year period. Very similar in shape. It's now losing ice at the rate of about 200 cubic kilometers per year. It has now become a significant term in the sea level rise equation. So again, this is evidence that, contrary to what you hear in the media, since 2000, not only has the warming continued, it's accelerated. And we see it in a whole different range of pieces of evidence, not just one. So the science has become ever stronger and ever more conclusive about what the climate system is actually doing. Here's the sea level rise data. Again, this Australian data, indeed the world data, comes from John Church's group in Hobart. And again, you see, not surprisingly, that if the ocean is warming, sea level ought to be going up. And indeed, it is going up. The Australian trend is very similar to the global trend. But again, I want to point out that if you look down here, since 1990, when we've had model estimates of how fast sea level should be rising, the actual data, which is the blue line, jagged blue line at the top, is actually rising right at the upper limit of the range of projections. Again, yet another piece of evidence that, if anything, we've underestimated how fast the climate system is moving. So the scientific evidence is absolutely clear. I want to talk a little bit then about the IPCC Fourth Assessment Report. You've heard a lot of criticism of the IPCC in the media. It's important to note we need to go to one more level of detail. The IPCC is not a monolithic single report. It actually has 3 working groups. Each one produces a report of about 1,000 pages. I brought along working group 1. That's all I could carry because it's pretty bloody heavy. The other 2 are about the same length. This is the 2007 IPCC working group 1 report. This is basic science. Now, if you look at the overall effort, there are about 1,250 scientists. Australia played its part in contributing. Reviewed by 2,500 expert reviewers, and they collectively submitted 90,000 comments on drafts. Now, I was one of the contributing authors to this report, and I can tell you what a painful process it was to go through every one of those comments, every one of them, and you didn't just have to deal with them, you had to write down and justify how you dealt with them, and it had to be made publicly available. There are 4 such rounds of reviews in the IPCC report. It is the most exhaustively, carefully reviewed document that I know of in the scientific world, or probably any human endeavor. This one, working group 1, this is the basic science on which policy is made. This document is 991 pages long. Do you know how many errors have been found? It's probably intensively scrutinized. The answer is 0, none. By people who are going through it trying to find errors. All the stuff you heard in the news about errors, most of those were beat-ups in the press. When you go back into the document, and it was working group 2, not working group 1. When you go back into the document, you find that they can be accused perhaps of not referencing properly, but when you track back to the original scientific work, it is peer-reviewed. And when you track back to the authors who wrote it, they say that the IPCC has represented it properly. There were two what I call peripheral errors. One was on the Himalayan glaciers. The other was on the amount of the Netherlands, which might lie below sea level. And by the way, the Dutch don't agree on that. So it's hard to hold the IPCC responsible for getting that wrong. So anyway, I think the bottom line here is there is absolutely no problem with the IPCC. It is the most exhaustively reviewed, the most heavily scrutinized scientific assessment document that I certainly know of in any area of science, not just climate. And to produce a document of 3,000 pages that has only 2 peripheral errors and none in the basic climate science, I think it's an amazing achievement. I want to point out that this is an assessment. IPCC does not do research. IPCC only assesses the research that's actually done. The research is done in institutions you know. It's done in CSIRO. It's done in the Bureau of Meteorology. It's done in the ANU. It's done in the other group of 8 research-intensive universities in Australia. And it's done in other universities and other research bodies, and similar bodies around the world. In fact, many of them are world-leading research organizations. They actually do the research. We are a major player in climate science. And in fact, when I was with IGBP for 6.5 years, looking over the entire international landscape, Australia was overrepresented when you compare to our population base in most areas of climate science. Our science ranks right up with the best. We rank up with NASA, with the best universities, Cambridge, Oxford, Max Planck Institute, ETH in Switzerland, anyone you want to name, we're right up with them. And we continue to make major contributions to the IPCC assessment. So I think you can rest assured that Australia's major scientific organizations that have a long, long track record of high quality control and high quality science are right in there making major contributions to climate science internationally. So, having said that, what does the IPCC Working Group 1, I emphasize Working Group 1, actually say? 3 things are important. These are the 3 big take-home messages on the science. Warming is unequivocal. That means we're 100% sure. The data is absolutely overwhelming, and the warming continues. I've given you some evidence just now. But other changes in climate, which are very important for the risks, are also occurring. Wind patterns, precipitation. I've talked a bit about sea ice. I've talked a bit about the big ice sheets. The last statement is very important. It is very likely, that means we're over 90% sure, and I'd probably venture to say over 95% sure, that greenhouse gas emissions are the dominant cause, at least since the middle of last century. Now that's about as close as you're ever going to get on an issue like this to consensus in the scientific community. Now there are many things that we still debate, like how fast the ice sheets might be lost and what's happening to Australia's rainfall and why. But this is the basis on which climate policy is being made, and on this, the science is settled. It is not debated in the credible scientific community. What are some of the risks then? Well, I've been talking a bit about sea level rise. This is an interesting image. The one on the left up here is Brisbane Airport. There's the runways and the terminal there, as it looks today. When you apply a simple inundation model with a 1.1 meter sea level rise, which is a plausible sea level rise, it's toward the upper end of the projections, but it's possible by 2100. When you combine that with a high tide and a storm surge like an East Coast low, that's the inundation you get. You can have your coffee in the second level of the terminal, but your plane won't be able to come in and go out because the airstrip's actually underwater. So this highlights that even under plausible projections in the relatively near future, we've got major pieces of infrastructure around the country which are vulnerable to the impacts of climate change. Ocean acidity. This is an interesting one. It gets tagged as a climate change impact, but to be quite honest, and this, I guess, betrays my original scientific training as a chemist, is that this is really a chemical effect rather than a direct climate effect. As CO2 dissolves in ocean water, it forms carbonic acid, which affects the concentration of carbonate ions, and thus the ability of organisms like corals to form their hard shells. And there's a lot of concern about coral reefs. Obviously, the Great Barrier Reef is one of the iconic ecosystems around the world, not just in Australia. So if you do a little chart of environmental space where you look at temperature change and carbonate ion concentration change, you can define a space where corals are absolutely happy, and in fact the environment between glacial, ice ages, and interglacial periods oscillates within this quadrant. But the quadrant we're heading toward, as we reduce carbonate ion concentrations and as we increase sea surface temperature, is this quadrant up here. We're already at point A. We're committed to going to point B, even if we could cut emissions to 0 tomorrow. And most projections show us going toward point C. Corals could not exist in the upper quadrant. It's an environmental space where they will not be able to form their shells. But what will happen is this. The ecosystem will convert. The structure will be around for a while longer, but the ecosystem will actually be an algae-dominated ecosystem rather than a coral-dominated ecosystem. It's quite a stable ecosystem, but it's not very popular with humans because it doesn't yield us as much fish or as many tourism dollars. So it will be a problem. Most marine biologists I talk to are very pessimistic about the future of the GBR without effective and rapid mitigation at a global scale. And I'll get onto that towards the end of my talk. Climate change and heat waves, and we've seen a few of those. And this is something that affects urban areas. It affects rural areas too, as whole areas of Australia experience very high temperatures. I just noted two of them, February 2004 in Eastern Australia. You can read what the data say. And I just want to note here that these high minimum temperatures at nighttime are particularly important for impacts on human health. It's the night after night after night of exceedingly high temperatures which actually eventually cause excess deaths, particularly in very young people and particularly in very old people. More recently, of course, we're familiar with the 2009 heat wave in the southern cities of Adelaide and Melbourne. This image comes from the Melbourne suburban train system. But in addition to the human health cost, over 200 premature deaths, more than the bushfires, by the way, in Victoria, there was disruption to transport here and also to power supplies. The Basslink connector between Tassie and Melbourne shut down. It actually wasn't a failure of the system. The system had a high temperature safeguard, which they didn't think would be exceeded until 2030. And it was exceeded in 2009, and interestingly, it was exceeded at both ends. It was also exceeded in the Tasmanian end. The frequency of these type of heat waves is expected to double by 2030 and treble by 2070. And these projections I'm giving you are with business as usual, as is if we don't get our act together. Bushfires, they're projected to become more frequent. In a way, that's a no-brainer. If temperatures are going up and you're having more extreme fire weather days, you're bound to get more extreme bushfires. And this is a projection of how the interfire interval for the Canberra region, here's the ACT, we're standing somewhere up in here, the city of Canberra. Under our current climate, this gives you an estimate of how often these large fires occur. Somewhere between 20 and 30 years, we can expect a pretty major fire up in the Brindabellas. But again, under a mid-range scenario, by about 2100, we can expect that to decrease to only 10 years or so, 10, 15 years between big fires. Basically, as fast as the forest can regenerate, they'll burn. Again, under a business as usual scenario. These all have implications for health, bushfires, heat waves, water supplies, and so on. And indeed, impacts on health are a very good integrator of a range of impacts of climate change. And I've just given you another example here. This mainly refers to northern Australia, although under severe climate scenarios, you could see dengue fever vectors coming down towards southern Queensland. This is the increase in the range of this mosquito which carries dengue fever. Currently, it's just up at the top end in Cape York Peninsula, but under a medium range scenario by mid-century, much of the Northern Territory now, and down parts of the north and central Queensland coast. Again, this is an impact which hopefully we can prepare for if we know that it's coming, but it nevertheless is a serious one. So that's a bit about the climate science and a bit about the risk to Australia of the climate changes that we might see. Another thing I want to mention, you've heard in the press about what a disastrous meeting COP15 was and how it was an utter failure and so on. I think that's an exaggeration. Certainly, many people, including many scientists, I think, were over-optimistic about what Copenhagen was going to achieve. It's by far the most complex negotiation humanity has ever attempted. Things like the World Trade Organization negotiations pale into insignificance in terms of the complexity of what this really means. Changing energy systems, changing economies, dealing with impacts, equity issues of who polluted when, equity issues about where the impacts are really falling. It's a really, really, really thorny issue. Nevertheless, there was an achievement called the Copenhagen Accord, and you may dismiss it as being non-binding. Indeed, it's not legally binding. But it's a very high-profile document. It was signed by leaders of countries, who were there in person, who put their personal stamp and their personal reputation on it. There were some significant advances. 80% of the world's emissions are covered in this. 35% are covered in the Kyoto Protocol. Agreement on the 2-degree guardrail, in other words, to limit the increase in global average temperature no more than 2 degrees above pre-industrial. The last two, I think, are really important. These are things that countries are already starting to move on. Establishment of a mechanism to support RED. Now, RED is an acronym for Reduction of Emissions from Deforestation and Forest Degradation. And RED plus is other forest-related activities, sequestration and so on. And also financial mechanisms to make this happen. The two big countries of interest are Brazil and Indonesia. But what this has done is it's reopened, I think, in a very positive way, the use of land-based systems to help us with this problem. Sequestering carbon not only in trees, but also in soils and other types of ecosystems. And I think although there's still some contentious issues about how this might be put into, for example, an emission trading system, the signal for Copenhagen was very big and very positive that these are important mechanisms and we need to move with them fast. The second major thing was an adaptation safety net, a recognition and agreement by everyone from the US through to the poorest African countries that climate change is really inherently unfair. That up till now, it's been the industrialized world, the OECD countries, which have been the major emitters. We're responsible for most of what's up there, 70 to 80%. It's the poor countries, particularly the countries in Africa, that are going to get clobbered by this and are being clobbered by this. So we need a financial mechanism to help them cope. There was a commitment of up to $30 billion for this 3-year period starting now, rising to $100 billion US dollars per year by 2020. And that's a lot of money. But interestingly, if you actually compare it to the money thrown at the global financial crisis, it doesn't look so big. Nevertheless, it's a very good start to dealing with some of these equity issues. But don't underestimate the challenge. These are the emission trajectories we need to have a reasonable chance to meet the 2-degree Celsius guardrail that was agreed in the Copenhagen Accord. So we're sitting here at 2010, we're emitting somewhere between 30 and 35 gigatons of CO2 per annum as a global community. The interesting thing about this graph is it's very sensitive to the peaking year. If we could somehow hit peak emissions next year, we then have to reduce by about 3.7% per year, which is a big ask, but it could be manageable. But by delaying the peak year to 2020, the emission reduction needed to get the same climate outcome becomes 9% per year. And that's a massive job for any economy. So really the crunch time, in my view, is the next 5 years or so. And can we really get our act together in that time? Getting back to the media then again, there are those views that have been put out there recently that all that I've just told you is nonsense and we don't need to worry and we can go back to doing what we're doing. So let me make a few comments about the science of the skeptics. And I've had a chance to have a look at this. Ian Plimer's published a book, for example, and some of the most vocal skeptics have been advising Senator Fielding. And I was asked to respond to a document that they produced on behalf of the minister. So for me it was an interesting and a reasonably straightforward task because in a university setting one of the things we do is we read PhD theses that are produced by our students and we read them critically to make sure they come up to the quality control that we expect at ANU and other universities. Using that sort of filter, I would have failed every one of those documents. In fact, I couldn't even get through them. They were so riddled with errors. And some of the errors are falsified and missing data. I can't say whether they were deliberately done or just done through incompetence, but they certainly weren't there. Improper use of statistics, using too short a period for averaging, using anomalous years to start your averaging period, and excessive use of blogs and other non-peer-reviewed sources as legitimate scientific sources. Very importantly, failure to understand climate as a system. And the last one, failure to create an alternative, internally coherent framework to explain what we observe, which is the real guts of science. You have to have an internally consistent, internally coherent framework if you're going to explain something and really think you know how it operates. And they utterly fail on this. A lot of internal inconsistencies throughout these documents. I'll give you some examples. The top one there is Bob Carter. The statement he makes now, of course, isn't a scientific statement. This is a statement that would, for example, come from an advocacy group. The middle guy you may have read in one of the Melbourne newspapers, I can't remember which one it was, or the Herald Sun. Andrew Bolt. Now that is definitely a scientific statement, but the problem is Andrew Bolt isn't a scientist. And the last one is Ian Plimer. Now, Ian Plimer actually has some very interesting perspectives because he comes from the long-term Earth system perspective. But in fact, and some of the stuff he writes is very interesting and quite good in that regard. But when he comes to contemporary climate science, he does what a lot of people who jump out of their own area of expertise do, makes a lot of fundamental blunders. So one of the things we do as a scientific community is we certainly check each other's credentials as we try to hire someone on the faculty and so on, as we try to appoint someone to a prestigious position. You ask for a CV. So if you look at the CVs, before I go to the CVs, I just want to make a comment about Plimer's statement, which is really interesting. Over very long periods of time, 500 million years, the Earth's environment has changed enormously. In fact, if you go back a little bit more, we've gone through a couple of snowball Earths, or at least slush ball Earths, where the Earth is almost completely frozen over. And we've certainly been in periods that have been much warmer than today, much warmer than the last interglacial. There are two problems. One is Homo sapiens has only existed for 250,000 years. We're a creature of the late Quaternary. Our physiology is locked into Ice Age interglacial cycles. The second thing is the rates of climate change, and this is one thing I want to point out. Here's the ocean acidity issue in terms of pH. Here we are in the year 2000. There we were at 1800, pre-industrial. You can see that the ocean has been more basic and it has been just as acidic about 25 years ago as it is in the year 2000. But if you look at a mid-range projection of CO2 emissions, this is the trajectory of ocean acidity on this time scale. And remember, evolution operates on long time scales. It doesn't operate on an annual time scale unless you might be an insect that can reproduce every 2 weeks or something. So the problem here is, yes, corals have operated in this range, but they have not experienced this rapid a change. Same thing for temperature. So again, beware of people who say, yes, the Earth has always been hotter or colder or more acidic or less acidic. And you can find periods when it has. But you certainly can't find them when Homo sapiens has been around. Nor can you find, with a few exceptions, times when change is that rapid. There have been times when it has been that rapid. And they're invariably linked with very high extinction rates, the so-called mass extinction events. And that should tell you something already. Okay, so summary of the skeptics' positions. Again, if you look at the record, some of them are well published in their own areas, but not in climate science. And that's the point. So, reasons for what's coming out? Well, I've read some material by media experts, and they claim that, well, there's pressure to sell newspapers, pressure to sell books. There are linkages to lobby groups that others have written about, for example, in the Climate Cover-Up book and so on. These are the two I want to talk about. Scientists are required to put forward our work in peer-reviewed literature. We have to undergo the quality control mechanisms that have been established for centuries that are the hallmark of good science. Everyone at ANU's got to do that. If we think we're going to get a promotion by writing blogs, forget it. That's not how science operates. You've got to do that. And the question I've got, and I'm not a journalist by any means, aren't journalists meant to in some way try to get at the truth? Are there any ethics or are there any standards that journalists ought to observe? There are some experts like Suzanne Moser, Max Boykoff, and so on, whose job it is, whose profession it is, academic profession, to study the media. And when you read some of their papers, you get some really interesting results. One of them is inappropriate application of the balancing norm. In other words, journalism has this strong norm that viewpoints should be balanced, which makes a lot of sense in politics in areas like that. It makes much less sense in science, where we don't operate. We have an evidence-based system. And interestingly, Max Boykoff has made the point that application of the balancing norm to something like climate change actually introduces bias rather than the other way around. It introduces bias because it gives an apparently equal voice to points of view which have not passed the quality control mechanisms of science. In fact, they've been discarded by the quality control mechanisms of science. A nice analogy might be sport. If we're reading the sport page, or listening to someone reporting on a soccer match and saying, it's very close, we don't know who's going to win, it's going to go into a penalty shootout, and then you ask what the score is, and it's 99-1. This is the sort of issue we're facing. And also, the public is largely illiterate about the processes and mechanisms of quality control. That's not meant to be a criticism. Should the general public know about all the intricacies of peer review, quality control, promotion processes, all this stuff that we do in academia? Or should at some point you do the same thing you do with your medical doctors, your brain surgeons, your experts and so on, and say, well, we trust that they've been adequately trained, they have a good education, and they're carrying out their profession properly. Same thing with scientists. If I took you to a scientific meeting, it would be hard to understand. It's jargon-filled, it's highly technical, and so on. But at the end of the day, there needs to be some level of trust in CSIRO, in ANU and the leading universities, in the Bureau, that we're actually competent to do the job. And particularly for universities, that we're competent to train the next generation of scientists. So is this really a failure of science communication? Have we as scientists somehow failed? Well, no, I think we're facing something deeper and more profound here now. I think the climate change debate has moved out of science only, into something more fundamental. Suzanne Moser has made a comment on it here, and you can read through that. And she's done some investigation that obviously there's some links to some big groups that feel threatened by the climate change issue, and that's part of it. I think it's actually even deeper than that, and I think there's a nice analogy here that we can look at. That's the analogy of evolution. Back in the 1800s, an English scientist named Charles Darwin came up with a new hypothesis of how life came to be and how it changes. And obviously it's the evolutionary theory, but it was very confronting for people at that time. Because at that time, the dominant belief was that we were somehow above all other living things. We were special. And Darwin said, no, we're just a part of nature. We're another ape, in fact. And that was highly controversial, and still is in some parts of the world. But that's how science works. It isn't beholden to the dominant paradigm of the day. It tries to understand the earth around us and understand ourselves as best we can. Evidence-based, challenging each other all the time. But sometimes we bump into strongly held views in society, and that makes it uncomfortable for science, and it makes it uncomfortable for society. But in the end, that's how we make progress. I think climate change has reached a somewhat similar level to Darwin's evolutionary theory. It challenges the relationship between humans and the rest of nature, just like Darwin did. Can humanity, can us very small 1.5 meter apes who run frenetically around the Earth's surface, or only 30% of the Earth's surface, actually affect the great forces of nature, the great geological cycles and so on? It just doesn't gel with a lot of people. It's very confronting. But in fact, the science is clear that we can in fact do this, and we are doing it. And so you take one step beyond that, and it starts challenging the implication, well, it starts challenging our view of what is progress, at least in a post-World War II world. Our way of life, our future. And this generates legitimate fears in people. Fears of the future, fears of what we might need to do, and so on. So I think that the climate change debate in society has shifted, probably in the last 3 or 4 months, certainly within the last 6 months, from being a peripheral environmental issue where science probably was the prime topic of debate, to one where science is being debated but as a surrogate for a much deeper debate, which is not really science-based. And I think that's what we're seeing, and that's why it's so hard for scientists to make any inroads now. I don't think it's because we're terribly poor communicators, although I'm first to say we can always improve. But I think there's something fundamentally deeper running in society. But I want to close on some very positive notes, because I think we can see our way through this and see it in a way that doesn't put us back into caves and back into a very primitive way of life. First of all, Copenhagen, the big disaster. Well, the truth is that the UNFCCC is only one of the ways we can deal with climate change. And as we speak, there are a whole range of different venues for dealing with the climate change issue. Bilateral initiatives, clubs like the G20, the G8 plus 2, the G8 plus 5, what have you. Other UN agencies, the World Trade Organization and so on, they're all taking up the climate issue in various ways. And in a way, I think this is good. This is a more resilient system of institutions and governance than a single monolithic UN organization. So there are positive things happening at multiple levels. There are positive things happening within countries. Within the US, for example, where a lot of cities and some states are taking action. Within Australia, in many different ways. So far from being a train wreck, Copenhagen was another step in one of the processes that we need to take. And we need to go ahead with the UN process, but in parallel and talking to the other processes. Well, what about reducing emissions? I've put some pretty daunting curves up. But in fact, this has been analysed by economists. Economists here at ANU, economists within the Garnaut Review, and actually the world's most thorough modelling was done by the Treasury here in Australia. They show this sort of effect on the economy. That as you go forward from 2010 to 2050, this is the global rise in GDP, using 1 as a standard number for 2010. Now, the baseline is the black. That's when we do nothing about climate change. The red line, just underneath it, is if we do some moderate action. We may try to hold it to 550 ppm, maybe 3 degrees or so. That has really an unnoticeable effect on the economic growth. The income of a person in January 2050 may be delayed by 1 or 2 months. They may be as wealthy in March 2050 as they would have been in January 2050, had we not had it. If you look at the vast reductions we need to really observe the 2-degree guardrail, yes, you see an impact. There it is, about 5% reduction. So you may be as wealthy in 2051 as you would have been in 2050. But the point is, you're vastly wealthier than we are today, no matter what. And this could actually solve the climate change problem. Okay. Now let's get more specific. What can you actually do? And this famous bottom-fold McKinsey graph is a really interesting one because it says, all right, the macroeconomics is interesting, but we actually have to do things. Change technologies, change behavior, and so on. There's a whole bunch of things we can do. And the interesting thing, this zero line is, above the zero line is where it costs to do something. Below it is where we make money, where we save money. Look at all the things we can do in society here, which will already get that curve tipping over, and it's actually going to improve our economic performance. Okay? And there are a range of things we can do which aren't that really expensive. And I suspect that as we learn about some of these new technologies like solar and so on, those costs will come down. So it's not a disaster story at all in terms of making the deep cuts we need to make. And there are technologies there. We don't have to wait for more technological development. We've got them. We know how to develop it. We know how to generate energy at large scales in a renewable way. Here's just one example. This is a solar thermal station in operation in Spain. But there are other technologies. Some people advocate nuclear technology, and new nuclear reactors are getting more efficient and cleaner all the time. There are other types of solar. There are other types of renewable like wind and geothermal. And there are very clever systems that get over the baseload issue. And they ask the question not as, do we need a big baseload power plant? They ask the question, can we deliver power reliably when it's needed? Because that's why you have a baseload. And the answer is, with smart grids, yes, you can do that. So all the technology is there. With renewable energy, we can have very comfortable, very fast land-based transport that runs on that renewable energy. This isn't something for the future. These are being rolled out at a vastly increased rate around Asia and around Europe. We know how to build buildings that are much more comfortable to work in and to live in and use vastly less energy. So the technologies are there, the economics are there, and so on. So what I want to say is the missing part of this story is that the transition we need to make is actually not a negative one. It's not going to drive us back to caves. It's not going to make us broke. It's not going to make us much poorer. It may, in fact, lead to enhanced lifestyles, cleaner energy systems, better health, and so on. So I think we need to turn the narrative around to one to say, yes, we have some transition challenges to make these changes. But in fact, at the end of the day, our grandchildren will be better off, just like we're better off than our grandparents. And I think if we don't make these changes, we may well be in a situation where our grandchildren are worse off. Because the consequences of not doing anything about climate change could easily be interpreted as doom and gloom. But it doesn't have to be. That's the whole point. I'm going to close now with a vignette. That's those of you who have been watching the weather news might have seen what's happened in the Northern Hemisphere. Here's a picture of Copenhagen during the second week of COP15. Here's another European city, and of course there's headlines, end of global warming. We've got this massive cold spell, Washington, D.C. under a meter of snow. Record cold in Beijing. You might think, well, these scientists have really got it wrong. Well, what should you do as a scientist? You have to be really careful with the data. So what you have to do is, all right, don't just look at 3 places around the world, Western Europe, Eastern US, and China. Look at the entire world, and look at the entire month. We can look at January. This surprises people. January 2010, it was the hottest on record. Now, I probably can't convince people living in Washington that that's true. But in fact, it's a very interesting number. Here's the temperature record for the entire planet. Lower atmosphere taken by satellite, so it's not contaminated by urban heat island effects and those sort of things. 3 pools of cold air, just off and along the eastern US, just in Western Europe. There's Copenhagen, there's London, and over in China. But look to the north of it, a massively warm pool of air across Siberia, across the Arctic, across northern Canada. Most of the southern hemisphere, well above average temperatures. You look at that globally, that is the warmest January since we've been able to get records. So, beware of extrapolating from a few points around the Earth, even though those happen to be critically important politically. So I'm going to close there, Anthony, and hopefully we have some time then for questions and discussion.